The famous Lucy was able to assume an upright posture, like modern people. Our 3.2-million-year-old ancestor could stand upright and move around like modern humans do. The scientists came to such conclusions after modeling the muscular system of Australopithecines, the most famous representative of which is Lucy. The new discovery reinforces the consensus among researchers that Australopithecus afarensis walked upright, not like a chimpanzee, using its arms for support. The reconstructed pelvic and leg muscles of Australopithecus also suggest that it may have climbed trees. This means that the species probably developed in both forests and grassy steppes of Africa. Lucy's muscles suggest that she was bipedal like us, and at the same time she was probably comfortable in trees, says Ashley Wiseman, a fellow at the MacDonald Institute for Archaeological Research at the University of Cambridge, UK, who carried out the modelling. The results and description of the research have been published in the journal, Royal Society Open Science. The Lucy fossils are the best preserved Australopithecus remains ever found. In the mid-1970s, Ethiopia recovered 40%. Her skeleton. The remains indicate that she was about a meter tall and weighed between 13 and 42 kilograms. The discovery also suggested that human ancestors may have walked upright long before larger brains evolved. When creating a model of muscles, scientists were guided by the structure of modern people. Our bone structure and muscle attachments may indicate how the muscles were arranged on Lucy's skeleton. Wiseman used digital modeling to recreate 36 muscles in each leg of the Australopithecus. The reconstruction shows that Lucy could straighten her knees and hips in a similar way to modern humans. This means that the species could stand and walk upright. The model also reveals the proportions of fat and muscle in Lucy's legs. It turns out that the legs of Australopithecines were much more muscular than those of modern humans and similar to the legs of bonobos, Pan-paniscus. While the human thigh is approximately 50% muscles, Lucy probably had 74% of them. Some muscles in her calves and thighs took up twice as much space as modern humans. Lucy's knees showed a wider range of motion than a human's. This, combined with its muscular mass, suggests that afarensis may have inhabited both dense forests and grassy savannas. Lucy probably moved in a way that we don't find in modern animals, Wiseman says. Although the discovery is based on an incomplete skeleton and it is not known how often afarensis was upright, the results of the analysis reinforce the scientific consensus about Lucy's physical abilities. Muscle reconstruction is a novel method of confirming bipedalism. It goes beyond the slightly simplified interpretations of paleontologists when it comes to inferring what movements characterized an extinct species, says Professor Fred Spoor, a researcher at the Natural History Museum in the UK. Muscle modeling has already helped scientists assess Tyrannosaurus walking speed and may shed light on similar traits in human ancestors. The climate crisis may fuel further pandemics. As the Earth's climate continues to warm, scientists predict that wild animals will be forced to relocate. They are likely to migrate to regions with large human populations, which will drastically increase the risk of transmission of zoonotic viruses to humans. This could lead to another pandemic. In their work, The scientists conducted the first comprehensive assessment of how climate change will affect the global virus suite found in mammals. The analyses focus on migrations that will be undertaken by species traveling to different parts of the world in search of new habitats. Because this is when the first encounters between different species occur, scientists predict that they could transmit thousands of viruses to each other. New research conducted by an international team of scientists led by scientists from Georgetown University on the link between climate change and virus transmission has been published in the journal Nature. According to the authors, animal migrations create greater opportunities for viruses such as Ebola and coronaviruses to appear in new areas. This makes them harder to track and makes it easier for viruses to transfer to humans. There are similar risks associated with the wildlife trade, said the lead author of the study, Drive. Colin Carlson, assistant professor at the Center for Global Health Science and Security at Georgetown University Medical Center. Gathering animals outside their natural habitat creates an opportunity for the development of the disease. Similarly, SARS went from bats to civets and then from civets to humans. However, the trade in wild animals itself is no longer unique. In the era of climate change, these types of processes will occur in nature almost everywhere, explains Carlson. It is worrying that animal habitats will move into areas occupied by human settlements, creating new hotspots where threats may spread. Many of these processes may already be taking place in today's world, and efforts to reduce greenhouse gas emissions may not stop the development and dependence. Another important finding is the effect that rising temperatures will have on bats, which are responsible for most cases of sharing new viruses with humans. Their ability to fly allows them to travel long distances and carry the largest number of pathogens. The greatest threat is expected in Southeast Asia, which is known for its bat diversity. At every stage, the simulations surprised us. We spent years double-checking the results using new data and assumptions. However, models have always led us to such conclusions. It's a truly astonishing example of how accurately we can predict the future if we try, says Carlson. Viruses are beginning to jump between species at an unprecedented rate. The impact of this phenomenon on nature conservation and human health can be staggering. This mechanism is another clue to how climate change is increasing risks to human and animal health, said study co-author Dr. Gregory Aubery of the Department of Biology at Georgetown University College of Arts and Sciences. It is not known exactly how these new viruses might affect the species that become infected. However, it is likely that many of them will create new threats to nature conservation and contribute to the emergence of new human disease outbreaks, Aubery points out. Research suggests that climate change will become the biggest risk factor for the emergence of a new disease. According to the researchers, animal migration is a bigger threat than more familiar issues such as deforestation, wildlife trade and industrial farming. The authors argue that the solution is to combine wildlife disease surveillance with real-time environmental change research. When the Brazilian bat reaches as far as Appalachia, we should find out what viruses are accompanying it, says Carlson. Trying to detect these migrations in real time is the only way to prevent the spread of new viruses and a possible pandemic, he explains. The COVID-19 pandemic, as well as the earlier spread of SARS, Ebola and Zika, show how dramatic the effects of viruses, jumping from animals to humans can be. To predict how this happens, we need to know how pathogens spread among animals, says Sam Shiner, Program Director of the U.S. National Science Foundation, NSF, which funded the research. This research shows how animal movements and interactions caused by climate warming can increase the number of viruses that are transmissible between species, explains Shiner.